Hello there, and thank you for joining me today as we discuss differential equations. We have two objectives for this lesson today. We will model relationships given in words using differential equations, and we will verify that an equation is or is not a solution to a differential equation. So let's talk about what a differential equation is to begin with here. A differential equation is an equation involving a derivative, hence the name differential equation. They are used to model situations involving rates of change. That's what a derivative is, right? And so some examples you can see down below. dv dt equals k times the square root of t. That's a differential equation. dy dx equals 4x minus 2. To the far right, x double prime plus 2x prime minus 35x equals 0. There's a second and first derivative involved there. Still an example of a differential equation. In order for us to model with differential equations, there's a couple of terms and ideas that we've got to review here first, and that is, a directly proportional relationship and an inverse proportionally relationship. So if we're told something like y is directly proportional to x, recall that means that y equals some multiple of x, so y equals kx. If y is inversely proportional to x, then it's an inverse relationship, more of a reciprocal relationship. So y equals k divided by x. So we'll look out for phrases like directly proportional to or inversely proportional to, and we will handle them accordingly. So let's start with a little bit of modeling here today. We're going to take the information provided on the screen here, and we're going to come up with a differential equation to represent the relationship that we're given. So a scientist is studying the relationship of two quantities s and t in an experiment. The scientist finds that under certain conditions, as the quantity of s increases, the quantity of t decreases. After taking measurements, the scientist determines that the rate of change of the quantity s with respect to the quantity of t present is inversely proportional to the natural logarithm of the quantity of t. Which of the following is a differential equation that would describe this relationship? So we've got to look through for some keywords and phrases, and the first thing we want to look for is one of those phrases like directly proportional to or inversely proportional to, and I see that phrase, where is it now? Inversely proportional to. So this entire sentence here is going to be important for us, and I'm going to highlight it in red. After taking measurements, the scientist determines that the rate of change of the quantity of s with respect to t present is inversely proportional to the natural log of the quantity of t. Let's take that and let's break it down here. Let's write an equation. It says the rate of change of the quantity of s with respect to the quantity of t. Well, the rate of change of s with respect to t could be written this way, ds dt. Now that word is here, and that translates to an equal sign. Then we have that phrase inversely proportional to. So we'll have this inversely proportional relationship like we saw previously here. And ds dt is inversely proportional to the natural log of the quantity of t. So that'll be a natural log t down here in the denominator because we have that inversely proportional relationship. But then there's going to be some constant multiplier k that we won't be able to solve for unless we're given more information. Well, the equation that I wrote here matches best with choice C. So we're looking for keywords and phrases just like we used to do when we were solving word problems back in Algebra 1, Algebra 2. Let's try another one. This one's got an added step to it where we'll actually be able to solve for that constant of variation k. This one says the population of a certain species of insect is given by a differentiable function p, where p of t is the number of insects in the population in millions, at time t, where t is measured in days. When the environmental conditions are right, the population increases with respect to time at a rate that is directly proportional to the population. Since we're here, I'm going to underline that. Starting August 15th, the conditions were favorable and the population began increasing. On August 20th, 5 days later, there were an estimated 10 million insects and the population was increasing at a rate of 2 million insects per day. Which of the following is a differential equation that models this situation? Well, we saw that phrase that I highlighted or underlined there. Let's highlight the entire sentence now. When the environmental conditions are right, the population increases with respect to time t at a rate that is directly proportional to the population. So in blue here, the population changes with respect to time t at a rate that's directly proportional to the population. So that'll be some constant times p, the population. Now, that's none of the multiple choices, right? Because now we're given some specific information that we can use to solve for that constant of variation k. And if I look at my multiple choices here, I'm not feeling so good about choice A. That one doesn't match up very well. But basically now the difference between B, C, and D is that constant of variation k. Is it 2/5? Is it 1/5? Well, even this one isn't right because there's a T instead of a capital P over there. So narrowing it down even further, is k 1/5 or is it 5? Well, we need some more information, and we're given that information here. We are told that 5 days later, the population is 10 million, and the population is increasing at a rate of 2 million insects per day. So in red here, if I write all that down, 5 days later, when t equals 5, we're told that the population is 10 million, and the population is increasing at a rate of 2 million insects per day. So all that information I just wrote in red came from the sentence that was highlighted in red. So we're now going to use that to solve for that constant k. So I'm going to switch colors here. Taking the blue equation, let's plug in what we know here. At this instant in time when t equals 5, the rate of change of the population is 2, and the population itself is 10 million. And we can divide by 10 here in order to solve for k, 2 divided by 10 being 1/5. Choice C is the correct differential equation that models this situation. So here's a problem where we had to take it one more step. We were given some specific information that allowed us to solve for that constant of variation k. So at this point, we have met half of our objectives so far. We have modeled relationships using differential equations. Now on to objective 2, we are going to verify solutions of differential equations, and we've got a couple of examples to practice that much. Got to put your differentiation hats on here because we'll be finding both first and second derivatives in this process. Here we go. For what value of k, if any, will y equals k times e to the power of negative 2x plus 4 cosine of 3x be a solution to the differential equation y double prime plus 9y equals 26 times e to the power of negative 2x? Well, so we want to know what this value k is such that the equation y works in this differential equation over here. Well, if that equation is going to be a solution to the differential equation to the right, then all of this stuff should be able to go in for y and make that equation true. The problem right now is that we've got this y double prime. So that means we're going to have to lace them up here, and we're going to have to find this second derivative here. We got a little bit of work to do. So let's do that. Let's take y and let's find the second derivative so we can make a substitution and check out if it works, or find what k needs to be in order to make it work. So let's find y prime first. Y prime will be equal to, the derivative here, our rule for e is to keep that e but then multiply by the derivative of the exponent. That's the chain rule there, where the derivative of negative 2x is negative 2. So that piece will turn into negative 2k e to the power of negative 2x. Now to the right, we've got plus 4 cosine of 3x. Well, our chain rule there, derivative of inside times derivative of outside, right? Well, the derivative of cosine is negative sine, so I'm going to have a minus here, okay? But then I'm going to have to multiply by the derivative of the inside here, the derivative of 3x, which is 3. And when I multiply that 3 to the negative 4 in front, I'll have negative 12. So there is our first derivative. There is y prime. Now remember, we need y double prime so we can make that substitution. So one more round of differentiation here. Y double prime equals, again, the derivative of all this. We're going to keep all of that, but we'll have to multiply by the derivative of that exponent, and that derivative is negative 2. And when multiplied to the negative 2 in front, that gives us a positive 4. So here's the derivative of that first part. Now to the right of the minus sign, the derivative of sine is cosine, so we'll have this cosine 3x. But then chain rule says multiply by the derivative of the inside there, which is 3, and 3 times the 12 in front of that term gives us 36. So there is our second derivative, y double prime, and that is what we're going to sub into this differential equation in the top right, and then we'll be able to solve for k to figure out what k needs to be to make this equation y a solution to the differential equation given. So let's go over here and let's make our substitutions, starting with y double prime. Y double prime was 4, oops, wrong writing utensil there, was 4k e to the power of negative 2x minus 36 cosine of 3x. That was y double prime, plus now 9 times y. Well, we were given what y was. It was k e to the power of negative 2x plus 4 cosine of 3x. And now equals, the right-hand side was 26e to the power of negative 2x. Got a little bit of algebra to do here now to try to figure out what k needs to be to make this equation true. And this looks like kind of a hot mess, but let's stick to our principles here. We're going to want to distribute this 9 so that we can use any of the terms in there. So this first group's going to stay the same. I'm going to copy and paste that here. There it is. Not doing anything with that yet. But now when we distribute this 9, we have 9k e to the power of negative 2x. This would then be plus 36 cosine of 3x. And again, this right-hand side, we haven't done anything with that yet. Well, let's look for some like terms we can combine. First of all, I'm seeing this minus 36 cosine 3x, this plus 36 cosine 3x. Those are like terms that are going to cancel each other out. Bada bing, bada boom. What do we have left here now? We've got a couple of like terms I've underlined that we can combine. Altogether, there's 13 of those. 13k e to the power of negative 2x. And on the right-hand side, that's still equal to 26e to the power of negative 2x. And now the goal here is to solve for k, isolate k. Well, we'll divide both sides by 13, and while we're at it, let's divide by 13e to the power of negative 2x. So k will equal 26 divided by 13 is 2. E to the power of negative 2x divided by e to the power of negative 2x cancels out. And all of a sudden, we have figured out what that constant k needs to be in order for y to be a solution to the differential equation in the top right. K needs to be equal to 2. Kind of an intimidating question right away, perhaps. At the end of it, it's mostly algebra here, besides having to find these couple of derivatives. We did need our derivative rules so we could find the first and second derivatives of y. Let's try one more here that asks us to do pretty much the same thing, but is worded a little bit differently. This one says, of the following, which are solutions to the differential equation y double prime minus 6y prime plus 8y equals 0. This one's going to take a little bit, right? We're going to have to kind of work our way through here and see which one of these, Roman numeral 1, 2, or 3, would get the job done here. The idea here is still the same, though. To verify which of these equations works in this differential equation here, we're going to have to make some substitutions. We've got a y prime, and a y double prime. So we're going to have to, again, do some differentiation here. Let's see if I can color code this. Let's start with the Roman numeral 1. There is y. Let's go ahead and find y prime so we can also find y double prime. Derivative of sine is cosine. I'm going to have that much. But then I got to multiply by the derivative of 4x, which is 4. And 4 times the 2 in front will be 8. So there is y prime for that Roman numeral number 1. But we also need y double prime. We'll have to make that substitution as well. The derivative of cosine is negative sine, so I'll have that with the 4x still. But then times the derivative of the inside, 4 times the 8 that was in front will be 32. So there's our second derivative there. Let's go ahead and sub that in right away. Let's see if that one works. Let's make our substitutions. I'm going to try to color code this and stick with blue. Here we are checking out Roman numeral number 1. So we start out with y double prime. That's negative 32 sine of 4x. Then minus 6y prime. Y prime was 8 cosine of 4x. Then plus 8y. Well, there, y was 2 sine of 4x. And now we have to figure out, does that actually equal 0 there? Well, let's clean this up a little bit. This negative 32 sine of 4x, let's leave this alone. This would be what? Minus 48 cosine of 4x. And then, I guess, plus 16 sine of 4x. Okay, and then does that equal 0? Well, we're going to have a couple of like terms we can combine here and here, but those won't cancel each other out, and we'll still have this left over as well. So this is not going to equal 0. We need everything to cancel out to equal 0, and that doesn't happen for Roman numeral number 1. So this one's out. Let's check Roman numeral 2. Let's find y prime first. The derivative of 3e to the power of 2x, well, we're going to keep that e to the power of 2x, but then chain rule says multiply by the derivative of the exponent, which is 2, and 2 times the 3 that was in front is 6. So there is our first derivative. Here's our second derivative now. Again, we'll keep e to the power of 2x, but then multiply by the derivative of 2x, which is 12, when you multiply 2 times the 6 that was in front. So let's check out Roman numeral 2 now. All right, so our differential equation starts out with y double prime. Well, for Roman numeral 2 here, that's 12e to the power of 2x. Then there's a minus 6y prime. Y prime was 6e to the power of 2x. You'll have to excuse me zooming in and out here. Plus 8y, where y was 3e to the power of 2x. And then again, does that equal 0? Well, let's see what we have here. 12e to the power of 2x. This is minus 36e to the power of 2x. This is plus 24e to the power of 2x. And when you combine all of those, these are all like terms, and sure enough, they all end up canceling each other out. In other words, that left-hand side does equal 0. Roman numeral 2 works. That's valid here. Y equals 3e to the power of 2x is a solution to the differential equation circled in red. Let's check out Roman numeral 3 here. I'm going to switch colors one more time. We'll need y prime first. Well, y is ce to the power of 4x. So our derivative then will keep e to the 4x, but then multiply by the derivative of that exponent, which is 4. And remember, there was a c in front, so 4c in front there. Our second derivative, y double prime, maybe you could work this through in your head. I'm just going to speed things up a little bit there. 16ce to the power 4x is what we would get. So let's see if then ce to the power 4x is a solution to the differential equation provided. So here's Roman numeral number 3 now, checking this out. We start out with y double prime, that's 16c e to the power of 4x. Then minus 6y prime, so minus 6 times, where y prime was 4c e to the power of 4x. Then plus 8y, where y was ce to the power of 4x. And again, does all of this end up equaling 0? Well, if you're looking ahead, you might already know the answer to that question, but if you don't, let's check it out. This would be minus 24ce to the power of 4x. This is a plus 8ce to the power of 4x. We have 16 and 8 more, which makes 24. Minus the 24 here, that all equals 0. So Roman numeral 3 is also giving us an equation that is a solution to the differential equation circled. So 2 and 3 are solutions. Choice D then is the correct choice. If you're able to do some mental math in your head and kind of crank that through, you might be able to do that much faster than I did here. I took my time just to go through some of that differentiation at a slower pace. So in our lesson about differential equations today, we had 2 solutions. We modeled relationships using differential equations, and we verified solutions to differential equations. Thank you for watching.